Okay, so for problem one, we're given two different radiuses, 2 millimeters and 1 millimeter. That's basically why I drew two different radiuses, and they're spheres, so they really should be 3D, and together they make the coalescence. And what we want is the pressure inside the droplet formed the coalescence of the two droplets. And so we use the volume formula of a sphere, which is 4/3 pi r cubed. And so we're using the r that we were given for both of the spheres. And together we got the value of 37.699 millimeters cubed, and I also converted it to meters. And you also want to solve for the radius. In order to do this, you isolate r and v. And basically that's how I got the 2.08 millimeters number, which is, and then I also converted it to meters. And then from this value, you want to find the total. You want to find the change in pressure. So that's why you you isolate the change in pressure. And the sigma value, it was given to us in lecture as 7.4 times 10 to the negative 2. We just found our total, and from there, that's how we get 71.15. And then we have the equation that change in P equals P internal minus P atmospheric, and we want P internal. We're looking for the internal pressure, which is basically just then the external pressure, and you have to add one atmospheric pressure, and the difference to get your answer. And so I isolated P internal, and my final answer was 101.40 kilopascals. 1B is very similar, but since you're in a bubble, you have an inner and outer surface, and they must account for basically, and you're using air and not water this time, but we kind of go through the same process. So I did the same volume formula, used the two radiuses and added them together, and got the same, I did the same radius as well. So that's pretty much all the same, but okay, so then, oh yeah, but this time you're using double the length basically. So that's why I multiplied by 2, because you're accounting for the inner and outer surface that you're calculating for. But volume is the same, again, radius is the same. And once you get this change in P pressure, then you use the same formula as P internal equals change in P plus P atmospheric, and you basically isolate P internal to then find your value. And then it also asks for the volume, so my value for that was 37 point, again, like the same value as I said before, and then 37.699 millimeters cubed, and then I also converted it to meters, so it would be in scientific notation. And then for pressure, I had 101.47 kilopascals. And then lastly, for number 2, so we're inside a box. There is ideal gas. Because this, we know that mass is going to stay the same. We know that pressure is going to stay we know that temperature is going to stay the same. And we know that R is going to stay the same. So basically, when we set these two equations together, those values will cancel out, and from that, we'll get P1, V1 is equal to P2, V2. So yeah, and then V1 was given to us as 1 meter cubed. P1 is the water pressure that's pressing down on the container, and then V2 is the volume of air inside the container, what is brought up, and P2 is just the P atmospheric. So because we know the initial volume, we use the formula that pressure is equal to rho G, and then Z2 minus Z1, which is just the change in height, and they give that to us because Z1 is 0 meters at sea level, and the top of the container is negative 100 meters. So that would just mean that the change in height is 100 meters. So from that we have all the values. Well, then plus the P atmospheric, we have all the values to then solve for P1, which is the water pressure that's pressing down on the container. So once you get that value, you have all your values. Because then again, V1 was the 1 millimeter cubed, the P2 is